Hello everybody and welcome back to yet another video on this series FEAP WAM discussions, and this is going to be a little short video because we are going to finish off with the geometric preliminaries what we have already started with, and most of the things we have already looked at, including the exponential map and various perspectives to view that relationship between SO3 group and S square. So today we are going to look at one more representation of the same exponential map, and also some expressions related to the some relationships related to the tangent spaces also, which will be used in the variation formulation of the energy equation. So here we have a small corollary where one-to-one correspondence between tangent space of SE square at lambda and S square at t is being described. So we know that if W hat it is an antisymmetric matrix and it belongs to a tangent space of SE square at identity, then W hat lambda belongs to a tangent space of SE square at lambda. This we know. Then we can see that W hat, which is an antisymmetric matrix, is related to a cross product. So W hat can be written as W cross, whereas W is the corresponding vector of this antisymmetric matrix. So if we take cross product W cross lambda E, if we multiply, okay, so we get W cross T. So this W cross T is the vector which belongs to a tangent space of S square at T. So lambda matrix causes the E vector to rotate and become T, and so that is how lambda is related to T, and W cross T is related to that T vector as it is lying on its tangent space. So this is the relationship between the two. So this will be used in the description of angular velocity when we will be writing linear momentum and angular momentum equations. So it will be used there. Moving ahead, we have one more expression, very important expression, to write the transform vector directly in terms of the original vector. Instead of writing first lambda in terms of its exponential map and then writing t is equal to lambda e or t dash is equal to lambda t, we can combine both the exponential map and this transformation t dash is equal to lambda t to get this relationship. So this is also coming from the same exponential map, but it is more direct. We are just writing the new position of the directorate, which is t dash, in terms of the original position t and the axis of rotation vector. So this expression can be easily verified, and I have written some derivation steps also which can be referred over here. Okay, and the same thing can be written when t is actually e, which is the original vector along the z direction in the Euclidean space. So both ways it can be seen that these are correct. One more thing to keep note, there are two vectors, one is theta bar and another is theta. So the one whose exponential map is being taken is theta bar, which is perpendicular to theta, is still in the Euclidean plane only, perpendicular to E, but it is a different vector. So there are two vectors, one which is acting like the axis of rotation and another the components of whose are being calculated in the FEM equations. So this we have to keep in mind. So at this point of time, we will just quickly cover one more important aspect of this geometrical transformation, which is given in part 2 of the series. You can see the title, this is part 2, and in the table 1 of part 2 we have this important relationship between t, lambda and e, which we have already seen, but a new way of understanding its result. So lambda naught matrix can be viewed as three column vectors t1, t2 and t. So if we have a vector t on which we apply the matrix lambda naught, here actually t and t naught are same. There's a typo here, there should be t naught. Okay, so if we apply lambda naught over e, we get t naught. So E is along the z direction. If suppose we apply lambda naught on E1 or E2, there should be an alpha also over here. So this is correct. This is T naught 1 and T naught 2 is equal to lambda naught E alpha, lambda naught E1 and lambda naught E2, and here we have T naught lambda naught E. So if we apply lambda naught over this E, then we get T1, T2 and T, and all these three are mutually perpendicular. That is one condition. That means T1 dot T2 equal to 0, T2 dot T is equal to 0 and T1 dot T is equal to 0, and all three are actually unit vectors. So in this expression, what T naught we have, that same T naught is actually coming over here. So sometimes lambda naught, which is actually 3 by 3 transformation matrix, is also written as lambda naught bar, just T1 and T2, by skipping the third column, because it is same as what was provided as input in the form of T naught. So this can be removed and it becomes a 3 by 2 matrix, and this 3 by 2 matrix can be used to transform the elements of tangent spaces also. So lambda naught is used to transform the vectors t naught or e to t naught or some t to t dash, but lambda naught bar can be used to transform tangent space vectors delta t, which is lying in the Euclidean space, okay, and small delta t is at the tangent space of the s square at t. So this is how it can be written. So we have completed the geometrical aspects of this Kosheret based shell theories. One question arises: what is the actual use of all these mathematics in this theory? So the main use is to write a singularity free description of director field. So we'll be extensively using these relationships to write the discretization of the director field when we have to write the expressions for updating algorithms for director field, its time derivative and spatial derivative. We'll be using these relationships. Plus, when we are writing the variation formulation, so there also, and also in the angular velocity expression, we'll have these expressions coming in. So this is highly useful relationship. And also, since in the Euclidean space we have only two parameters, you can see here e1 and e2, or theta 1 and theta 2, we have only two variables in the Euclidean space, and these two become three when we transform it to the shell configuration, any general vector t. So basically we can move using this geometrical transformation, which is seamless and singularity free. We can easily transform 2 degree of freedom to 3 degree of freedom. So adding 3 degrees of freedom of displacement, it is easy to move from 6 degree of freedom to 5 degree of freedom. We know already that the 6 degree of freedom, which is the rotation about the director axis, is redundant, and it is not possible or very difficult to find out a corresponding director stress. stress factor which is along the director, which would rotate that director. So that is something which we cannot find, so it is difficult to it is not a good idea to have that existing in our model. So it is best to remove that redundant degree of freedom, and this is how it is done seamlessly. So I hope this will be clear. So we'll be stopping for this video now, and we'll be continuing with the kinematic description and the balance laws in the next video. Thank you.